This is Labor Day weekend, so I know this is our big chance to rest before we work really hard for the rest of the semester. So, and let me just try to think if there's anything. My audio is working. Are there any questions? So as usual, I want to remind you, read the notes. If you read the notes, if you read the notes and you have anything that you find confusing or unclear, you find any errors, please mark them and turn them in to me, okay? I really appreciate that because I try to make improvements in them. And are there any general questions? Has the reading of the notes been going okay? So I guess I'll pick up today. What we want to do is I want to finish up some of the stuff from the. I know that chapter 2 is sort of jam-packed with a lot of material, particularly if you haven't had a lot of background in probability. So make sure you try to learn that as best you can and go through. You're supposed to do actually all the homework problems basically from the end of that chapter. Okay, and some of them are more sort of highly technical aspects. If you can't do all the most highly technical problems, at least try to simplify it down to something that you can do, okay? And if you have any questions, a few people have emailed me with questions, and I try to answer them by email, or, you can come and ask me. If you want to ask me after class, or you can set up an appointment. But off-campus, probably email is the best way to go, but it's up to you. So now what I want to do is I want to go on to I want to finish up some of the material, so I'm going to go to the document camera. Is that what we're doing? So what we hadn't talked about is random processes. Random processes. What happens is that discrete-time random process. So last time we talked about Bayesian estimates, and this is just sort of a summary that you have an original signal, and the measurement that are independent and with independent identically distributed noise. So if you were just going to compute the maximum likely estimate, so this is the measurement with noise, and the maximum likely estimate is just exactly the same thing. There's no difference at all. But if you, in this case, if you apply a model of the distribution of the signal, okay, then you can get a much better estimate of the original. It's not perfect, but it certainly has the characteristics of the original signal, right? This signal doesn't even look like that signal. It is spectrum of the noise. Okay, so, and it works out the example. Now, this sort of begs the question of random processes. So we're talking about random variables. So what's the relationship between random variables and random processes? Well, random processing is just collections of random variables, finite or infinite collections. Yeah, so we'll only really be dealing primarily. I can't actually think. Maybe at some point we'll deal with continuous random processes, but we'll mostly be dealing with discrete signals, so discrete random processes. So n is a member of a discrete set of integers, okay, and x of n is a random variable. So here we have a countably infinite number of random variables. We say it's a random process. So it's a simple enough definition, but then there's a lot of ways that you can build on this to say interesting things. One thing that comes up is well, how do you model the distribution? This is sort of a technical condition, but it's kind of interesting in that if you have a finite dimensional vector, then you can just look at the finite dimensional cumulative distribution function, and then that quantifies the distribution of the random vector. But what if you have an infinite? Now, this may be like, oh, well, I don't really care, but okay, if you worry about such matters, if you have an infinite number of random variables, so you have a countable, so you have like a discrete time random process that goes from minus infinity to infinity. Then how do you write down the distribution of that? Well, you can't write down the distribution because it's a function of an infinite number of variables. So it turns out that what you could do is you can write out all finite dimensional distributions, okay? And then what you do is you can show that if you know the distribution of every finite dimensional distribution for this infinite sequence of random variables, there's a thing called the Kolmogorov extension theorem, which is the gigantic sledgehammer, okay? And you can take, if you have any sigma field like this, which is dense in the set of all, if you have a sigma field, and when you have a dense, I think, a subset of it, then you can show that it can be completed. You can extend basically the measure to the larger set. So it turns out that knowing this is enough to know the distribution is a complete infinite random process. That's probably a detail that many of you never thought about before, and maybe won't again, but it's kind of good to know. It makes you feel warm at night and cozy to know that you're safe, and all the distributions of all infinite dimensional random processes are well defined. And then, now, there's the concept of stationarity. Now, a lot of students get really locked up on stationarity, okay? And it's really such a simple idea once you understand it. But it's one of these things where if I write the definition down, the definition looks really complicated. But the concept is very simple, okay? So the definition is that it says that, okay, if the distribution of the random process, so this is the distribution at, say, you know, the time, at specific times, okay? So, so it's the time, so you have a finite, you have a discrete time random process, and this is the finite dimensional distribution between time m and m plus k, okay? But if you shifted that to time 0, its distribution is the same. So what does that mean? That means that if I have a random process, the intuition behind stationarity is this. So you have some random process. So let's say it's a random process, okay? That's a random process. If I take any time window in that random process, that the distribution inside of that time window is the same no matter where the time window falls. So as I slide this time window around, I have the same distribution. Does that mean that the random process is equal in different time windows? Of course not. It just says its distribution is the same. Okay? So let me give you some examples. If I have the random process, which is that, say, x of n is equal to the sum from I equals 0 to n of xi, okay? And let's say the xi are IIDs, so they're independent and identically distributed with Gaussian random variables with mean 0 and variance 1, okay? So if that's xi, okay, so then Sn is the sum. So this is called a random walk, right? Random walk. You've probably heard of this. And what it means is that, I'll back out a little bit so I can see it all at once. You know, you start off at, say, 0. You know you always start at 0 because at time 0, it's a sum from 0 to, maybe I'll make this n minus 1 or something like that. So you have no terms in there, right? And you start at time 0, right? At 0. And then you take some random step. And then you take another random step. And, you know, like this, okay? Now, is that stationary? Is a random walk stationary? So it's really a discrete time random process, but I'll draw it like this. Okay? Is a random walk stationary? So is the distribution of the random process the same no matter where the window is? No. Because clearly, if I showed you a window, if it starts at time, if the first sample is 0, then chances are the window is starting at time 0. In fact, the probability 1 is the thing starts at time 0. Because it is possible for another sample to be 0, but the probability of it being 0 is the probability that a dart hits pi. Okay, so the probability is 0. So this is not a stationary random process. It feels like something's invariant. Actually, it's stationary increments, but it's not a stationary random process. Okay. Okay, so that's what it means to be stationary, that the distribution of a sliding window is the same, okay? Now, in addition, we have a thing called the second order random process, which is a process where the mean is finite and the second order expectations are finite. So if you take the square or you take the correlation between any pairs of random variables, they're finite. So if it's a second order random process, okay, then it means that the mean and covariance is this. Okay, they're well defined. And if we say something's y-10 stationary, it means that the mean is not a function of time, and the covariance, or I guess is this called the time autocovariance is what I call it, is not a function of time. So does that mean it's strict sense stationary? Not necessarily, because it might be that the mean and covariance are not a function of time, but some higher order moment is, okay? Or some higher order, there's some higher order dependency. If something is strict sense stationary, doesn't mean it's y-sense stationary? Yeah. Well, you'd think so if it was the world was, but in fact it's not actually the case, because that was a trick question. If you answered yes, your heart's in the right place, okay? But it's not for the following technical reason, which is that you can have a strict sense stationary random process that doesn't have finite, that has undefined mean, right? Its expectation could be infinite. So you could have, if you know what a Cauchy random variable, you could have so for instance, you get independent Cauchy random variables, okay, that with the same variance, or not variance, they don't have any variance. If you had IID, independent, identically distributed Cauchy random variables, that would be a stationary random process, but it wouldn't be second order. It wouldn't be y-sense stationary because it's not a second order random process. That's sort of a technical detail. If it's stationary and second order, then it must be y-sense stationary. Okay. So everybody understands what stationary means. Okay. Now reversible is a little bit more subtle, and reversible is a little bit of a tricky term because it's used in this class and in the literature in slightly different ways, okay? So if I say a random process is reversible, okay, what I mean is that if you take the random process and you reverse it in time, that its distribution is the same. So it looks the same, its distribution is the same, playing forward and backward in time. Now, we're also going to talk about random. So I'd like to give the example of speech. Okay, I think there's actually a problem in the homework where you have to come up with a non-reversible random process. I know a lot of people have trouble with that, but it's really easy. Okay, so how do you come up? Well, first of all Gaussian random processes are reversible. Why? Because I think I have a proof here. I have a proof here. Okay, well, first of all, okay, it's in here, but I'll just do it. First of all, if I know the mean and covariance, if I know the mean, so let's say that you have an xn, right, it's a random process, and let's say it has mean mu and covariance r of k, auto time covariance r of k, okay? And it's Gaussian. If I have a Gaussian random process with mean mu and covariance rk, right, then I really know the distribution. Because from this, I can always write the finite dimensional distribution down. Why? Because if I take any finite window, from the autocorrelation, I can compute the correlation between any pair of random variables, right? And I know what the mean is. Without loss of generality, I can just assume the mean is 0. I could subtract it off. From that, I could compute the autocorrelation. I can compute the covariance matrix R, right? So from R, then I can write down the distribution P of X, okay? Right? Now, so if I know the mean and covariance and autocorrelation, I know the distribution of the random process. Now, if I take a Gaussian random process and I reverse it, so if I take y of n equals x of minus n, if I reverse the random process, then it's got the same mean and covariance, autocorrelation, right? Because autocorrelation is actually always a symmetric function anyway. These are real random processes. So, therefore, it must have the same distribution, P of x, right? And if it has the same distribution, then, you know, that means it's reversible. It's a reversible process. Okay, so, if you look at a Gaussian random process, like generate a Gaussian random process, it's easy enough to generate a Gaussian random process. What you can do. So in your computer, generate a sequence of xn of IID n01 random variables, okay? Take xn and put it into a filter, h of n, right? And that will produce an output y of n, okay? And, you know, by changing this filter, you get a different Gaussian random process here, wasn't it? If you look, this is always a Gaussian random process. How do I know? It's got to be a Gaussian random process because it's a linear combination of Gaussian random variables. It has to be Gaussian. It has to be jointly Gaussian random variables. If I say Gaussian random variables, I mean jointly Gaussian. Okay? So this is a jointly Gaussian random process. If this is stationary, this is a stationary random process, then that has to be a stationary random process too. That's easy enough to show, and you can calculate the autocorrelation. Actually, the autocorrelation R of k is just going to be equal to h of n involved with h of minus n. So it's the correlation based with itself. So yeah, so this has got to be a Gaussian random process also, right? So you can produce Gaussian random processes pretty easily this way. If you look at, and you can try this in MATLAB, it's really easy to do. If you look at that signal and you plot it, you'll get something that kind of looks like, I don't know, it'll look like something. Who the hell, oops, I'm sorry, I didn't say that, okay? I said, it'll look like something. And then it'll look like this, okay? And then what'll happen is you plot it and you reverse it. Of course, okay, that was not a Gaussian random process. That was not well modeled by Gaussian random process. Human beings are really bad at producing random variables, okay? That should be a project in class, okay? Ask somebody to produce an independent sequence of random variables, say ones and minus ones, okay? And then once you get that sequence from them, you can analyze it and you'll find all kinds of really strong dependencies, okay? Because human beings are just really bad at being random. Unless they're administrators. Okay, so if you reverse this, okay, you'll get, and it'll also pretty much look the same. So, Gaussian random processes are reversible, okay? Now, for your homework problem, you have to produce a non-reversible Gaussian random process, okay? So how are you going to do that? Well, this is how you could do it. Produce something like this. Okay, you have a sequence xn, and xn are IID. Now I'm giving you a homework problem for this. Okay, so they're IID, right? And the probability that xn equals 0 is equal to 1 minus 2 epsilon, where epsilon is a small number. Okay, and the probability that xn equals 1 is equal to epsilon. And the probability that xn equals minus 1 is equal to minus epsilon, right? So it's just a small probability. So when it comes out, is you go along, and all of a sudden, you get like an output, right? And you go, you see, I'm really bad at generating random variables because if I want to generate binary random variables, I want to make them like different, okay? But real binary random variables, there would be a pretty good chance that it would have been the same, okay? Should that be epsilon too? You mean its value?
No, the probability.
Yeah, the probability should be, what's that for? Yeah, we can't have minus probability, okay? Thanks, someone's awake. Now, what you then do is take xn and put it into a filter, say h of n, where, say, h of n is equal to u of n times, I don't know, 0.9 to the n. So, okay? And then what will happen is that what will the output y of n look like? Well, it will look like this. it'll look like, it helps with the sound effect, like that, you see? And it'll go, is that a reversible random process? Does that random process look the same going forward as backwards? You can tell very easily whether that random process is going forward or backwards, right? Why? Because obviously it's got these little decay things, right? And the orientation of the decay things is going from left to right. So if I reverse it, it's obviously not going to be a reversible random process. But this is not a Gaussian random process because X is not a Gaussian random process. So I haven't violated the assumptions of my proof, okay? These kind of models could be used for speech. Does speech sound the same going forward as it does backwards? No. It sounds different, right? I've done this imitation before, but I won't do it this time, unless it's popular demand. But anyway, yeah, speech. Okay, that will be an assignment. To imitate speech going backwards. You have to do a little recording of that and hand it in for the homework. Okay. Now, so we got Y-sense, we got reversible random processes. Oh, and then the last thing is we got power spectrum. Okay, now what's the power spectrum? Well, I guess there's some details here, but basically what happens is that to calculate the power spectrum, there's different ways to define the power spectrum. Okay, I use approaches that I like or whatever. Okay, but I define the power spectrum as being the expectation of the Fourier transform, the magnitude of the Fourier transform of the signal. Okay, but and then I say a theorem is that the power spectrum can be computed as the Fourier transform of the time autocorrelation. Okay, you could also take that as the definition of the Fourier transform and then prove the other thing is a theorem. Okay, but I felt like doing it this way. So, in practice, this is what you do. You calculate the autocorrelation of the random process, and then you take a Fourier transform, and that's the power spectrum. Okay, and let me see. I think here, power spectrum. Okay, the power spectral density of a zero being White-Sense stationary electron. Okay, the distribution of a White-Sense is uniquely specified by its power spectral density. Why? Because if I know the power spectral density, I can take the inverse Fourier transform and I get the autocorrelation. If I know the autocorrelation, then I can compute the correlation, the cross correlation between any finite set of samples in the random process. If I know that, I can write its distribution down. If I know the finite dimensional distribution of any, if I know all finite dimensional distributions of the random process, I know its overall distribution. Okay, so it all fits together. It all works, and then you can extend this to two dimensions. You can have a two-dimensional autocorrelation, and you can have the two-dimensional discrete space power spectral density, which is the discrete space Fourier transform of the two-dimensional autocovariance. Okay? And you can do that in more dimensions, I guess, too, right? Yeah.
Can you elaborate on that? Why S1, S2 is equal to X of S1 minus K1.
Okay, which one now?
That's like
this one here?
No, it's the last paragraph, the third line of the last paragraph.
Okay.
The third one. Yeah, that equation. Why S1 S.
Oh, this one here?
Yep.
Okay, so in other words, I'm saying that if I shift the random process by K1 and K2, and if that always has the same distribution, independent of the choice of K1 and K2, so it has all the same finite dimensional distribution, then the random process is stationary, and it's reversible. Okay, if I can just reverse it. This is a time reverse right there, right? Now, if it's so normally, I think that I was careful about this, but normally, actually, some of the definitions on this are a little bit. it's a little bit dicey. 2D reverse. Yeah, the definition of reversible.
Yeah, the definition of reversible is like, it's fine, but I think the stationarity is...
Okay, so yeah, I wanted to point out something here, which is I think, okay, so the definition of reversible, every reversible random process is stationary, okay? Because if you look at the definition of reversible, what I'm saying is, okay, so I've reversed here the, this goes from T0 to TK, and this goes from TK to T0, right? But I'm also saying that this is true for all integers n. So, in general, a sort of a sub-assumption of this is that any reversible process has to be stationary. Okay, so the definition of reversibility here is including stationarity, okay? You know, there's different ways of doing that. It's an important detail. And there's another thing I should point out, that later on we'll talk about Markov chains, and there's a concept of reversible Markov chains, okay? And they're a little bit different. Reversible Markov chains don't necessarily have random processes which are reversible as their outcomes, okay? And the reason is that in a Markov chain, the concept of reversibility is a little bit different. There what you're saying that if you wait long enough, the random process it produces will become reversible. So there could be some sort of transient at 0, and then it reaches some sort of steady state, and then if you wait long enough, it'll be reversible. That's for Markov chains. You can worry about that later. When we get to there, I'll have a more precise definition. But I just wanted to warn you that the word reversible is used a little bit different in the context of, a little bit differently in the context of Markov chains. You don't even know what a Markov chain is yet. So, okay. Any other questions? You look like you might have another question. Okay, now, so the next thing, I'm going to switch to the computer. The next thing we're going to do is we're going to start with chapter 3 and causal Gaussian model. Okay, so now just to go back and motivate what we're doing here. Remember, our objective in all this is to solve inverse problems, or at least one of our objectives is to solve simple processing problems, many of which are inverse problems. And very often when you do that, you want models. So we need to have different models, okay? And it turns out that one of the most important things when you're doing these models is prediction, okay? So, okay, let me, I don't know. Let me go to the document camera again, okay? So, well, let me just go to me. Can I? Because I want to just. Why is it not working? Okay, yeah. So, prediction is very important, okay? Because in modeling. So when you want to model something, you want to say something about how it behaves, okay? And it turns out being able to predict something is very closely related to modeling how something behaves. If you think about it, you know, I like to think of it in the context of people, okay? If you feel like you know a person very, very well, okay, then you feel like you have a good idea of what they would do in different situations, right? You might not necessarily know exactly what they're going to do, but you have some sense of what range of things that they might do, right? So that's like causal prediction, right? So you feel like, I don't know how maybe your parents, like, you know your parents were already, so I knew they would do that, okay? Okay, so prediction is very closely related to modeling, okay? And later on we'll talk about Markov chains. In Markov chains, what we actually do is we actually model the conditional distribution of each new step given the path, okay? But the first thing we're going to do is we're going to do the Gaussian case. In the Gaussian case, you can limit yourself to linear prediction, okay? So there's a few different kind of major themes we have here. One is causal prediction, okay, versus non-causal. Okay, so in causal prediction, you have, say, a 1D random process, and you're going to use the past to predict the present, okay? And then the other possibility is that you have non-causal prediction. Okay, and in non-causal prediction, you have the past and the future, and you're going to use them together to predict the current, okay? Okay, so that's causal and non-causal, okay? Then you have 1 and 2D, okay? 1D and 2D. 1D and 2D prediction. Okay. Okay, so you have 1D and 2D prediction. Okay. In 1D prediction, you say in 1D you have a set of points like this, right? And you predict, say, a point like this if it's causal prediction. And in 2D, you have like this. Okay? And you need to, or you might have non-causal prediction. And here, you have to predict a point from all surrounding neighbors. Okay, so it's sort of like predicting inward like that, right? Now, it turns out that, can you actually see that on the board? Yeah, I think that's good enough. It turns out that 2D is fundamentally different from 1D. And the reason that 2D is fundamentally different than 1D is that when you remove one point in a line, you disconnect the line, okay, topologically. But when you remove one point in a plane, you don't disconnect the plane. So that turns out to have like fundamental implications. When you go to 3 dimensions or 4 dimensions, things pretty much stay the same as in 2. But 1 is distinctly different. And there's a set of different tools that are commonly used in 1 dimension that don't work in 2 dimensions. Okay? So that's why this is an image processing course and not a signal processing course. Okay? So there's that. Okay? And then the other thing is we have Gaussian versus non-Gaussian. If it's Gaussian, well, we know about Gaussian random variables, okay? Yeah?
How do you determine the 2D non-causality?
Yeah, so in 2D it will be non-causal and, see, these are like different flavors, okay?
Okay. But I'm saying like in 2D, how will you get the non-causal part? Like it's coming from...
So in 2D, okay, so this is a really good question. See, there's going to be a lot of interactions between these things, and the interactions are going to be really important. It reminds, there's this game, is it called Causal or something, where you have like, everything is a binary vector, okay? So you know, you can have, you know, say this is like, there's 2 possible states here, causal and non-causal, and 1D and 2D, and Gaussian and non-Gaussian. And you can have any of these combinations, okay? So your question's a very good one. And I'm sort of showing the non-causal case here, but you can also have the causal case. So in 2D, you could just have, you would have to order the points, okay? And we're going to talk about that, and only use the points that you had in some causal ordering to predict, okay? In 1D, causality is fairly natural. In 2D, causality is really disturbing, okay? So that's another thing that happens, that in 1D, okay, you can live with causality, and it turns out that a whole broad class of things, okay, it turns out that in 1D, causal models are very general, okay? So you don't really need non-causal models in 1D for the most part. Sometimes people use them because they're convenient, but mostly you don't need them. You can do everything with causal, okay? But when you go to 2D, it turns out that, well, first of all, causal models are a little bit strange, okay, because it's like, well, what does it mean to be causal in 2D? But then, even when you do it, it turns out it's much less general than the non-causal case. So that's what a lot of this class is going to be about, okay? It's going to be about talking about how you generalize things to, well, we're going to start with the 1D causal Gaussian case, which is the simplest, okay? Then we're going to go to the non-causal Gaussian 1D case, okay? Then we're going to go, okay. So I think the way, the order we do it is we first do, so let me see. So we need like a hypergraph is the problem here, okay? Because we have 3 dimensions, right? So we have let me not try to do it right yet because we don't have enough blackboard space. I'll do it on this thing in just a moment, okay? But we're going to go through, there's basically 2 possibilities to the 3rd power, right? So that means there's 8 combinations, right? So there are 8 combinations of things we can do, and we'll more or less do all 8 but it gets a little bit tedious. But we're going to do it in an order, okay? And we're going to start off with causal 1D and Gaussian, okay? It's like a hypercube. Does anybody know what a hypercube is? They used to talk about a lot in computing, right? Where they had hypercube architectures, right? And it's like a hypercube. So we're going to start off at the base of the hypercube, right? Yeah, there's 3 bases. I'll have to draw this. Oh my gosh, I'm a really horrible artist. How did I get that to look so bad? But anyway, we're going to go out on this hypercube, on the vertices of this hypercube, right? So, but it turns out that when we go to 2D, non-causal models are much more general. And that's what a Markov random field is. Have you heard of a Markov random field? So a Markov random field is a 1 or 2D non-causal model. But it's mostly interested in 2D because that's what's really powerful. And then we're going to bring in the non-Gaussian, because real images are not Gaussian, okay? But we're going to start off in the simplest case, and the simplest case is going to be causal, 1D, and Gaussian, okay? That's where we're starting right now, okay? So it's going to seem simple and boring a little bit, but it's very important, okay? So let me go to the document camera. So really what happens is that it's like we have causal, non-causal, okay, and it's really bad. Actually, I have it right here. I've actually done this. Okay, so we have causal and non-causal, okay? And then we're going to have 1D, 2D, right? And then we're going to have Gaussian and non-Gaussian, right? Okay, so the first thing we're going to do is we're going to do causal, 1D, and Gaussian, okay? Then we're going to do causal, 2D, and Gaussian, okay? And I think that's still chapter 3, right? Then what we're going to do is we're going to do non-causal, 1D, and Gaussian. Then we're going to do non-causal 2D and Gaussian, and this is going to be the Gaussian Markov random field. That's important. We're going to use that. At this point, we're going to take a breather because you're going to be really bored, and we're going to go off and solve a problem, which is doing an image restoration. Well, actually, you'll write a lab, okay, in MATLAB, do some image restoration using this Gaussian, sort of a Gaussian Markov random field, okay? But then we're going to conclude that we're dissatisfied with this, even though we've done a lot of work, because it doesn't work as well as we'd like, okay? And we're going to say, well, we have to go to non-Gaussian models, okay? So then what we're going to do is we're going to do, well, we could go through this whole thing with non-Gaussian, but at this point it would be a little tedious. So we're going to kind of accelerate the pace, and we're going to go to, from this point we'll be non-Gaussian, okay? But we'll go to non-causal, and we'll do, we'll do causal, and we'll do 1D, and this will be a Markov chain, right? Because we'll do causal 1D and non-Gaussian, that's like a Markov chain, and we'll do non-causal, and we'll do 2D, and we'll do non-Gaussian, and this will be a Markov random field. It'll be the general Markov random field. And then, at this point, we'll do another lab. We'll actually do the first lab, and we'll do a better job on it, okay? Well, we'll use non-Gaussian. So this is sort of where we're heading. We want to do the non-causal, 2D, non-Gaussian, the Markov random field. That's kind of where we're heading, okay? And that's the thing that's going to actually pay off. But we kind of have to do this first, or I think you won't understand it very well, okay? So that's where we're going. It's kind of a roadmap. Now, if we want to predict something, if we want to model something, we want to be able to predict, okay? So, as I said before, if we can predict something, it usually means we can model it, okay? So, we have a random process, and we're going to use the past values to predict the present value, okay? Now, if it's a Gaussian random process, and we want to look at the conditional probability of xn given xr for r less than or equal to n, right? Now, what do we know about the conditional, if it's jointly Gaussian in the process, what do you know about the conditional probability of this pixel given all the previous values? What form does it have? This is a Gaussian random process, so what form does it have?
A times x plus constant.
So it's, well, first of all, yeah, I know what you're saying, okay, I'm putting in a little different word. What type of distribution is this? It's got to be Gaussian, right? Because we know that the conditional distribution of any random variables, if they're all jointly Gaussian, then the conditional distributions have to be Gaussian. And in general, this is a little bit floppy notation. So it'll be normal, right? And it means, what's the expected value of xn? It's got to be what kind of a function of the past? These are all jointly Gaussian. It's got to be a linear function of the past. So it'll be some kind of linear operator here, a times x, and I'll put this less than n, that's the past, okay? Plus, it could be some constant too. We'll say beta. If by the way, it's a stationary random process, then a and beta can't be a function of n, because then it wouldn't be stationary. To be stationary means the distribution of everything, it doesn't change with time. So if the distribution changes with time, then it's not stationary, right? So if it's stationary, a and beta are not going to be functions of n. And you're going to have some variance. We'll call it sigma, I don't know, squared, okay? I'm not feeling very imaginative today. So, okay, and this is also not a function of n. So that's something we know, right? Now, so then if we want to characterize this sample here, all we need to know is A, the prediction, this linear prediction operator, and sigma squared, the prediction variance, right?
In the probability of xn should be a strict equality, r less than.
Oh yes, I'm sorry, otherwise they would be back to the peanut butter. Right? Right. Then the answer would be obvious, right? Good. Now, so now what happens is this. You can say, okay, so the conditional expectation of xn given x less than n, so that's the past, right, is we know it's going to be a linear operator. So I'll say this is Gaussian and zero mean. Because I don't feel like having to deal with mean, okay? So if it's zero linear mean, and it's also, let's say, stationary, you're going to read the notes, right? Because I'm doing a special case here, but the notes are a little more general, right? If it's linear mean and stationary, and let's say this is infinite, then what will happen is this is going to be equal to the sum from I equals 1 to infinity of xn minus I times hi, okay? Why? Well, first of all, it's got to be a linear operator, so this is the most general linear operator. Second of all, the linear operator cannot depend upon time because it's stationary, okay? So, the notes, read the notes, okay? They'll work this out a little more, okay? So basically, it's a linear time invariant filter applied to x. It's got to be the minimum mean square error predictor, right? So this all is going to result in the conditional expectation, which is the minimum mean square error predictor, which I'm going to denote as x hat of n. So that's the minimum mean square error estimate x given the past, right? Now I can also write down epsilon n is going to be the prediction error. So I take xn minus x hat of n. The difference is the error in my ability to predict. So if these are my parents and I know them really well, I'm going to get an accurate estimate of what they're going to do next. If I don't know them so well, then my estimate may not be so accurate, right? But this, I'm going to use the minimum mean square error estimate predictor. Okay, and okay. Now what we can do is we can show, and this is really amazing, okay? You can easily show, and it's in the notes, okay, but you can go through it, is that these prediction errors, xn are actually IID with mean zero, Gaussian with mean zero and variance sigma squared, where sigma squared is the prediction error. So the amazing thing here is that causal prediction errors are always uncorrelated, and if it's Gaussian, they have to be white. Because if a series of Gaussian random variables are zero mean and uncorrelated, then they're independent. So uncorrelatedness for Gaussian random variables is equivalent to independence. By the way, it's very important, I don't know if I mentioned this to you before, but it's very important you read the notes. Why? Because this class is like this. Did you ever do a Rubik's Cube? You like have this little thing and you turn it like this, and it's very simple. You just turn these little things, okay? You're trying to get it back again, and it's really hard. Okay? So in this class, I do a lot of little simple logical steps, but I string them together in very complicated ways. And when I get to the end, you might say, oh, like, I don't quite understand how we got here, okay? It's sort of like me driving around with my GPS. It says go left, go right, and then I'm lost, okay? So you need to read the notes in advance so that you've thought this all through. So as I go through these sequences of logical steps, it's clear in your mind and you can follow, okay? Now, so we can actually show that the prediction errors are independent, identically distributed. Because they're independent, identically distributed, I can write their joint distribution down. So I can write the joint distribution, I don't have much more time, epsilon n, okay? Now, the interesting thing is this, the epsilons can be represented as a vector times the a. It's actually going to be I minus a of x. So there's a linear transformation that takes you from the x's to the epsilons. So if I can write down the distribution of the epsilons, I can also write down the distribution of the x's. And the transformation here has a determinant of 1, so the multiplying constant of the Jacobian is 1, okay? So it's really easy. I'll just switch over. I don't know if we have 30 seconds. I'll switch to the PC, and you can write down the distribution. So you have to go through all this. It's not that complicated, really. And you can write down the distribution of the random process in closed form from this predictor. So what's the upshot of this? The upshot is goodbye, and I'll see you next time, because there's no more time. Bye.
Okay.
Okay, so,